next speaker, Stephan Wagner, back from Graz now. Yeah, thanks for coming, Stephan.
Thank you very much for the introduction, and thank you for joining for this talk. So I'll be talking about a model of random graphs that I learned about recently, and it's got the name depth-centric tree sources. I'll tell you in a moment what this is all about. It's from a paper by John, Young, and Kiefer from 2014, where they defined this model. They call it tree sources because it's in a sort of information theoretic context. The depth-centric, as you will find out in a moment, has to do with the fact that maybe somewhat unusually for random trees, we don't generate them so much by some number of vertices, but by what is usually called the height. So what you need for that is some family of probability distributions that can, in principle, be rather arbitrary. It's given by sigma, two-parameter function, which has this property that the sum of sigma ij over all pairs ij, whose maximum is n-1, needs to be 1. So this defines a probability distribution on the set of all pairs whose maximum is equal to n-1. You need to do that for all positive integers n. And the intention of that is that you recursively construct trees, binary trees to be specific. In principle, you could certainly extend this model to non-binary trees in a suitable way, but I'm sticking to binary trees here for now. A binary tree of height n, so a tree where the greatest distance from the root to a leaf is equal to n, is constructed by first determining the heights of the two branches. Now, to get a height of n, one of the two branches needs to have height n-1, and the other cannot have greater height. So that's exactly why we defined the sigma the way it is defined. For n equal to 0, you just say the tree is a single vertex, and other than that, you recursively generate your trees by first picking a pair ij according to the family of probability distributions mentioned above. And then once you have settled on a pair ij, that's the heights of the two branches, left branch, right branch, you recursively construct a random tree of height I, a random tree of height j, and then just attach them to a common root. That gives you a tree of height n. To give you a very simple example, let's say we want to construct a tree of height 3, so not too tall. And let's say on the first step, the random pair that we generate is the pair 1, 2. It could have been any of the 5 pairs 0, 2, 1, 2, 2, 2, 2, 1, and 2, 0, but suppose it is 1, 2. That means that the left branch will be a tree of height 1, and the right branch will be a tree of height 2. Now, for the left branch, we don't really have to do much more because it isn't actually very random anymore. There is just this one tree that possibly works for us. But on the right, there are still several possibilities. And we can say that the random pairing question is now 1, 0. So we will have a tree of height 1 on the left, a tree of height 0 on the right. Now, again, there is only one possibility in each case. So the tree on the left has to look like the tree on the left here. And the only tree of height 0 is, of course, the single vertex. Yes? Sigma sub n, sort of, yes. However, I mean, the n is kind of automatic because you take the maximum of I and j. Yeah, of course. So for each n, you have a probability distribution that is given by these sigma ij's. Yeah. So you're, of course, correct that the sigmas restricted to this condition form a probability distribution that you might want to call sigma n. However, I believe that this is the actual notation used by the three authors of that paper. And actually, I'm going to change it soon anyway. So I haven't said anything about the probability distributions yet. There could be anything. But in order to be able to say meaningful things, I believe one has to restrict to special cases. Otherwise, it gets too complicated. So first of all, I would like to make the assumption that my sigma is symmetric. That wasn't part of the definition, but I think it's reasonable to say that sigma ij should maybe be the same as sigma ji. And then I ignore left, right, and just say, well, I take a probability distribution for every n on the set 0, 1 up to n minus 1. That's for the sort of shorter branch. And the taller branch has to have height n minus 1 anyway. So that's a slight simplification. And then I construct a random binary tree of height n following the rules that I just explained. So for n equals 1, the tree is just a single vertex. And then for n greater to 1, yeah, you generate a random variable whose distribution is exactly this Pn. That gives you the height of the shorter branch. Then recursively construct the tree of height n minus 1, a random tree of height xn, and then you attach them to a common root. And that's your tree. Still, this is maybe too general because your Pns could still be anything. The first thing you might want to try is then, well, what happens for the uniform distribution? So for each n, you uniformly take a number between 0 and n minus 1, and that's the height of the shorter tree, and the taller tree will always have height n minus 1. So what can we say about things like the size, the distances, other structural properties of the tree? So for example, occurrences of certain patterns, anything that has been studied for other random tree models is now up for grabs here. All right, so the first thing that you probably want to know is how many vertices will a tree of height n have under this model. And if you set up a probability generating function, then you can actually very quickly get this recursion. Of course, you have your one subtree with a height of n minus 1, and then the other subtree, anything between 0 and n minus 1, each with a probability of 1 over n. So you immediately get that. And you can get rid of the sum if you want by, oh, sorry, hang on, what did I do now? There we go. You can get rid of the sum by saying, well, I multiply the n across and the f n minus 1 across, and then you have a sum, and then you take the first difference of that sum once, and you got yourself a recursion that has somewhat more complicated terms maybe, but on the other hand, it's only a recursion of 3 terms, and there is no more sum in it. All right, and then you can differentiate set x equal to 1, and that gives you a recursion for the average size of the tree. So far, so good. This is the kind of thing that people who like analytic combinatorics thrive on. You've got a recursion. You can turn this into, well, first of all, an actual explicit equation. It turns out that this recursion has been studied. You can also set up an exponential generating function, as we will see in a moment. So as a matter of fact, the mu n here is up to the factor of n factorial, something that's known, the number of partial permutations of n elements. So partial permutation means that you just have a subset that you permute. Also, number of rook placements on an n by n chessboard, where you don't necessarily have n rooks, but k rooks. So there are a bunch of combinatorial interpretations of the sequence. So all of this is quite well known. The exponential generating function is known, and you can apply the saddle point method to it. And what you get is this. The average size of the depth-centric random binary tree in the uniform case is asymptotically this. So the most important part, the take-home message, is maybe the e to the 2 square root n. Right. So you'll find that in the whole talk, there is no theorem. I'm sticking to propositions. There is a simple reason for that. All of this is very much work in progress. So I've really just started, and I hope that maybe on some later occasion, maybe next year's AFA or so, I'll be able to say a lot more. Right, but one thing that one might wonder now is, well, this is the average. Is this also somehow the typical size, right? It could be that with very low probability, the tree gets very large, and that somehow skews the mean, whereas more typical trees have much smaller size. So the next thing to try to investigate is, what about higher moments? What about maybe a limiting distribution for this? And indeed, that is possible. So if you continue this analysis with higher moments, it turns out so higher moments satisfy an asymptotic formula, and the asymptotic formula looks like this. So you see your mu n, the mean to the power k, and then some coefficient ck. And these ck's are constants, and one can determine the constants. I'll say a little bit more about them in a moment. But they form this sequence here. One can explicitly compute, and they're all rational numbers. Originally, I found them as a recursion, but one can also characterize them in other ways, as we will see. So what this tells us is that if I normalize by mu n, then this normalized random variable has moments that converge, and it turns out the moments are characterizing the distribution. So you have convergence in distribution to some random variable with that moment sequence ck. It doesn't seem to be any of the more well-known moment sequences. At least I don't think it's a standard distribution, but maybe it is the case. One fun fact is that if you take the associated moment generating function, then it satisfies a differential equation, which is rather lengthy. But somehow if you substitute in the right way, then you end up with this differential equation, which is a lot more compact and can even sort of be solved. So you can get an implicit equation for that, but involving a nasty integral. So I don't think it's necessarily very helpful, but it's maybe a cute little detail on the side about this distribution. But more to the point, so I know now that the order of magnitude is indeed typically that of mu n. So if the size of the tree is typically order of magnitude e to the 2 square root n, then if I turn this into an expression of the height in terms of the size, it would mean that if the size is n, then the height is of order log n squared, which is different from most, but not all random tree models that are around. So the main types are those where it's either log n or square root n. This is somewhat in between. It's not unique at that, but as it turns out, one can do something more there. Log n squared is not the only thing you can get with this model. Okay, so let's make this a bit more general. As I said, one shouldn't be overly general, because then I don't think one can say very much about the model at all. But here is an attempt to do it in a slightly more general way. I take a sequence, and we will choose some rather natural sequences for that. And we choose the probability distributions in such a way that Pn of I, so the probability that the shorter branch has height I, is proportionate to AI. So it needs to have that precise probability there, AI divided by the sum of the A's up to n minus 1. Okay, so then what we have studied so far, the uniform case is, of course, the case where A is constant. Okay, what is next after a constant sequence? Well, one might try things like powers or exponentials, and we will do just that. So for geometric sequences where AI is q to the I, basically q equal to 1 is somehow the most interesting case after all. The three phases are q less than 1, q greater than 1, q equal to 1, maybe not surprisingly. So if q is less than 1, then that means the probabilities decay exponentially. So this favors trees where the smaller tree, the smaller branch of your tree is really small. So much smaller than the other. It follows essentially a geometric distribution. So it's of constant order basically. And then it turns out that the size of your random trees only grows linearly with n and is also asymptotically normal. So it's somehow not so interesting. The uniform case is what I've just discussed. Q greater than 1, on the other hand, favors trees that are roughly balanced. So the shorter branch will then also almost have height n minus a little bit, and the little bit is also geometrically distributed now. So here the size grows exponentially with n. If one wants just the mean and an asymptotic formula for the mean, one could in principle do the same things as before. It's possible to set up a recursion, get this recursion generalizing the one from before. And that simplifies using the same trick as before to a rather short and compact recursion. And then in this recursion, you immediately see the three possibilities that are occurring. Case q less than 1, q greater than 1, q equal to 1. If q is less than 1, then the final coefficient there tends to 1. And your recursion essentially looks like this linear recursion with constant coefficients that leads to linear growth, plus an exponential error that doesn't matter very much. Yeah, q equal to 1 is something we've already seen, and if q is greater than 1, then this quotient tends to 1 over q, and the size grows exponentially. So in this case, I'm not 100% sure yet what the actual limit distribution is. My first guess was maybe log normal, but now I'm not so sure anymore. We will see. So some heuristics about this. So again, I've alluded to that already. If q is less than 1, then there's typically a large branch, height n minus 1, and a very small branch, following approximately a geometric distribution. So you're adding something that's in expectation constant in each step. And so you expect something that's normal. So repeating the argument, the typical shape of the trees is like one long path, and attached to that, a sequence of small trees. And these are almost IID random variables. They are neither completely independent nor completely identically distributed, but pretty close. So it's not maybe not surprising that you would get linear growth in the central limit theorem. And this still works even for sequences AI that go to 0 sufficiently quickly. For q greater than 1, again, it's precisely the other way around. Large branch of height n minus 1, and the small branch that is not much smaller. So height n minus h, where h follows a geometric distribution. And the size of the two branches are the same order of magnitude pretty much. So it's like multiplying by a constant, by multiplying by a random factor each step. That's not entirely true, but you can convince yourself that at least heuristically you should get exponential growth. All right. I'll also say very briefly something about powers. So this is maybe a bit more interesting because the behavior is not that extreme. So there's more gradual transition, perhaps. And one observes different phases. So if k is less than -2, we're in the situation with linear growth that was mentioned before. So I said that if the AIs grow, if the AIs go to 0 sufficiently quickly, then we're still in the linear case. The sufficiently quickly means that the sum I AI is finite, and that happens exactly for k less than -2. Between -2 and -1, one observes a stretched exponential. So stretched exponential is this e to the some power of n, where before we have observed the square root of n, but now with a different value of k, the exponent is not 1 plus k half. Yeah, no, that's correct, actually. I was briefly wondering. This is not greater than 1 because k is negative. So you get an exponent that's between 0 and a half, somewhere for k between -1 and -2 and -1. The borderline cases at -2 and -1 are a bit special with some additional log factor nastiness, but I'll skip those. So the interesting thing is that you've got this exponent of with a 1 plus k over 2 there. So if you remember, when we had square root n in the exponent in the uniform case, it meant that relative to the size, the height was log n squared. And now you can get log n to some other powers using this. For k greater than -1, you're in the stretched exponential case as with the uniform random variables. So the exponent is constant times square root n. Lastly, I would like to say a few things about parameters other than the size. So the external path length, or you could take internal path lengths or total path lengths just as well, they're all related. The external path length is a sum of the distances of the leaves from the root. So this says something about how the vertices are distributed, how far they are away from the root. In the uniform case, I'll show what's happening. You can set up a bivariate probability generating function, go through the motions, and then find that the mean external path length has a nice explicit exponential generating function, which is pretty. And then from that, you can do your saddle point analysis and find that the average external path length in the depth-centric random binary tree with uniform probabilities turns out to be the mu-ins, the average size times n half. So this indicates a fairly even spread of the vertices somehow. Because the height of the tree is n, and on average they're in half away, so to say. All right. Of course, as I said, there are many other parameters that one could potentially study, and one could also try much more general or different probability distributions for the piece. This is really something that I think has just begun, and I expect to encounter a lot more nice surprises there. But I think my time is up now. So thank you very much, and I'll be happy to answer questions.
Questions for Steph?
Hi, Stephan, thank you. I have a quick question about the case of power sets. So does it make sense to consider K positive?
Yes, I mean, you're just taking the probability is proportionate to I to the K.
Yeah. And do you know what you get then? Or?
And then the K positive was included there. So
It was? So I must have...
So K greater than -1 includes positive K.
I see. I see. Okay. Thank you.
Thank you for your talk. At some point, you mentioned that the expected number of nodes in your tree was counted by the number of partial rook placements on an chessboard.
Yeah.
Would you have some intuition or like combinatorial interpretation of this fact, or any explanation?
Well, so the recursion we got has an interpretation, and in fact, there are several other combinatorial objects that are counted by the same things, and you can interpret the recursion in a suitable way, and that gives you a sort of bijection between the two. I don't know anything better than that. But I mean, this sequence really has many interpretations. I was surprised to see. So if you go on the OAIs and check the sequence, there are, I don't know, 8 different things mentioned immediately, all somewhat equivalent. So, yep, Jim.
Sorry.
So Stephan, thanks also for the talk. Do you think that, I have 2 questions. One is, do you think that this might be a good model for some sort of real world phenomenon? That's one question. And the other was, I think you were explaining that for, if you take AIs other than the uniform case, you still get limiting distributions, but I don't think that was explicit. So the question is, do you get limiting distributions?
I have not actually worked those out yet. So except for the case where you have a normal distribution, I haven't worked out any explicit limiting distributions yet. No.
And what about the first question of
real world phenomenon? The real world, I know too little about the real world. But I mean, from a purely mathematical point of view, I think it's fun to create models where you get some unusual height behavior, right? So you're away from the log and square roots and get some more in between things.
Okay, let's thank Stephan one more time.